Okay, hello everyone. Welcome to another episode of Science and Technology Q&A for kids and others. So I've been doing these Q&As ever since the pandemic started, and they've been gradually evolving a bit over time, but I just encourage people to send questions about anything, about how things work in science and technology, and I'll see what I can do to answer them. Maybe we'll talk a little bit later about some ideas that we have for changing this up a bit and see what people think about those. All right, I see we have a bunch of questions left over. So I see one here. Why do flies fly around seemingly constantly with no apparent goal whatsoever? Well, I think I can say more about the philosophy than the biology of that. The flies, I think, so what is the fly thinking about? Well, I suppose that they're, a very basic question. The fly, like many creatures, is probably foraging for food, and there are all kinds of different foraging patterns that different kinds of creatures use. I mean, sometimes there are creatures like, I don't know, caterpillars. They're famous for, they'll go in to consume a leaf, and you'll see the track of the caterpillar, and it goes in this curve where it's trying to sort of consume the whole leaf. And it's kind of a fun thing because, you have to imagine this question about how do you snake that sort of path that the caterpillar is following so that it eventually covers the whole leaf. It's kind of the same type of problem as if you're numbering zip codes in the US from 0000 to 99999, whatever. How do you snake those numbers around the US? They're mathematically those kinds of things where you're kind of snaking a curve through a whole space are called space filling curves. And there are a variety of different ways you can sort of design that space filling curve. Often these fractal nested patterns are a good way to do it. But caterpillars use a very junior version of that. And I think different kinds of animals, there's a whole notion of foraging theory, which is this whole question about, if you're a creature and you want to sort of get all the food from a particular area, how do you move around the area to get all that food? It's the same kind of question. If you're a robotic vacuum cleaner and you're trying to clean every part of a room, how do you do that? And do you like systematically go one line and then the next line scanning through the room? Or do you go like in a spiral shape and try and cover the room that way? And so there are these different kinds of systematic foraging techniques. I suspect that flies, if they are doing something where they are trying to find things, they may have a simpler technique that's more of a random walk, because if you say, imagine the robotic vacuum cleaner, and it's trying to clean the room. So one thing it could do is just scan back and forth, make a spiral, whatever else. Another thing it could do is just randomly zip around the room. And chances are that eventually, if it zips around the room for long enough, it will find most pieces of dirt that are in the room. Now, in fact, in that particular case, because there are boundaries to the room and corners and things, the chance that it will get into a corner is lower than if it was systematically exploring the thing. But for a creature that's sort of foraging, that's a possible approach. Now, an interesting question is, another reason for critters to do sort of random stuff is because they want to escape a predator. It's like if you always did the absolutely predictable thing, then you would be your predator just has to learn, well, if you go to the right of the creature will go to its left. Okay, so cut that off and get it from the right. It's the same kind of thing if you're imagining some, AI-based robotic tank or something, and when this happens, it always does this. Well, the enemy can then go and use its AI system to be smarter than the first AI system and, blow up the tank or whatever. So it's this idea about do something random and unpredictable can be useful it's like, I don't know, when people, at least in movies, when people are like, running away from something, and it's like they run kind of randomly, sometimes run back and forth, and that doesn't seem to me to make a lot of sense. But if they sort of ran randomly, it would be much harder for the thing to hit them than if they run, in a very predictable pattern. So an interesting question would be for a fly, how does it make its randomness? How does it in its brain how is it? Is I think its brain has, we have like 100 billion neurons, and I think a fly has only over 50,000 neurons maybe in its brain. I think that's about the right number for ants as well. You know, it's got those complicated eyes. It's got these compound eyes, not like our eyes, where, you know, in our eyes we have a lens where we're focusing the light to make an image on our retina. And for a fly, it has these little ommatidia things where it's got a whole array of them. It kind of got that idea from trilobites back in the Cambrian period or something, where there's this whole array of different sort of tiny little micro eyes, and it's just using those to figure out. And when light gets into one of those things, it has the same kind of photoreceptor at the end, but it doesn't have a focus. It doesn't have a lens. You know, you don't see flies wearing glasses. Well, it's kind of a silly idea anyway. But it would not. It will be a different kind of thing, because it's not focusing light in the way that we are, where we're taking the whole image, putting it through a lens in our eyes to focus in our retina. So in any case, from the fly's eye, it's getting some visual information about the world. And then presumably it's deciding whether to fly, whether to turn and fly this way or that way or the other. How does it figure that out? And how does it make a decision, to now I'm suddenly going to zip left, now I'm suddenly going to zip right? I'm not sure. And I think it's an interesting question, how sort of randomness is generated in the brain of the fly. I did look at this once, maybe 25 years ago, so I'm not sure if things have been done on it since then. At that time, not much was known about it. I mean, it's similar to the question of, in biology, there are certain kinds of things that we know kind of what the source of them is. Like, for example, let's say a heartbeat, or let's say a walking motion. We kind of have an idea that there are things in our brains that are kind of oscillating back and forth. It's kind of like an electric circuit you can make an electric circuit that will just oscillate like in a sine wave. And it's the same general type of thing that's happening. There are many kinds of neural processes, as well as chemical processes, that will just tend to have this cyclic behavior. That's sort of what it's often called the central pattern generator, which is the thing that kind of lets critters walk. I mean, walking, has a very definite periodic motion. You're kind of, you can walk. I mean, even if your brain is not, even if lots of things aren't functioning properly, you can still successfully walk. For us bipeds, it's more complicated. We have to keep balance and things like this. But in general, the legs are moving will happen at a pretty low level in the nervous system. It's complicated when critters like for us bipeds, we're either walking where there's always one foot on the ground, or we're running where we end up with in the middle of running, you've got sort of the definition of that as both feet are off the ground for a little bit. If you're a quadruped, four-legged critter, then you have basically four modes of walking, depending on whether the legs are going sort of in phase on the two sides, right feet forward, left feet back, or whether you have a situation where the right foot is back and the left and the right front foot. Whether the front and back feet are going in together or whether they're going oppositely. And that's the difference, walk, trot, canter, gallop type thing. Gallop, I think the feet come, the front and back feet are coming inward, outward, as opposed to going in phase, so to speak. But anyway, and then the obvious question is, if you're a millipede, where there are mathematically, you can work out how many different possible in phase, out of phase, legs on one side, legs on the other side, things happen in a millipede, and it's some astronomical number. But in fact, millipedes basically, I think, have two modes of motion, either where the legs on the opposite sides are going kind of out of phase or in phase. And I think you can even see if you like have a millipede walking along and you like touch it at the back of the millipede, you'll see this kind of wave going up the legs as the millipede decides to speed up. And it kind of has to, it's very much like, reminds one of kind of the propagation of I don't know, electromagnetic waves or something, or any of these kinds of waves where the front of the millipede the back of the millipede has changed and the front of the millipede has to change to agree with that. And there's a wave that propagates at a certain speed as that fact about the change in speed kind of propagates down the millipede. So In any case, a few thoughts about the question of flies. Now another question would be, you see a fly flying around, what is its goal? What is its purpose? How do we find that out? You know, we see some famous example of these, what are they? These kind of pufferfish things that I think they exist in the ocean off Japan, among other places, where they'll spend a few days and they'll make in the sand, they'll make this incredibly elaborate pattern. It looks like one of those mandala patterns where the sand is all piled up in this very elaborate way. It's kind of an art form type thing. And the little fish will make that pattern. It's a huge pattern compared to the size of the fish. And then it'll destroy the pattern. And it's like, why did the fish make that pattern? And you know, you might say, well, let's use evolutionary biology to try and understand it. Maybe the fish is illustrating that it's a very well-functioning fish, and so mates for that fish should come, and then there'll be a fitter, you know, fish children and things from this fish who's been able to make this amazing pattern, and you know, that's a possible theory. But if we ask the question, how do we know why the fish made that pattern? That's a very difficult question to answer. It's a difficult question because if we say, why do we humans do what we do? It's like, why do I do these live streams? Why do I, you know, why do I, okay, if you say, why do I eat something? Well, it's because if I didn't eat, you know, I would starve. Why do I eat? Why do I do, I don't know, why am I writing some elaborate document right now about some obscure kind of very beautiful system, kind of a numerical multi-way system? Why am I writing such a document? Well, there's a whole chain of stories about, well, I find it fun and it's useful for this and I'm learning about that and so on and so on and so on. But I've got this whole chain of explanations of why am I doing this? And that chain of explanations ultimately kind of plugs into a whole sort of cultural story of, well, you know, we're at this time in history when things are, this thing is happening and that thing is happening, and you know, we understand the value of intellectual ideas and et cetera, et cetera, et cetera. So in the end, this why are we doing something, you know, plugs back into the whole sort of story of our history and the history of our civilization, et cetera, et cetera, et cetera. For the fish, what is that story? We have no idea. And it's, you know, we can give these kind of evolutionary biology explanations, but if we say kind of from the point of view of the fish, why is it making this pattern? Who knows? You could say, oh, it is just a mere reflex of the fish that it makes that pattern. But, you know, you could say that about a lot of things that humans do. It is a mere reflex that we choose to, I don't know, write giant essays about things because we are merely filling out our sort of reflexive built-in feature of, you know, communicate or something. You know, you can make up those kinds of stories, but the sort of the real answer to the sort of the how do we understand the purpose of the fish, for example, in the end, the only sense of purpose that we really understand is the one that we have and that's tied into our sort of cultural history and all that kind of thing. So unless we can make that translation to the fish, it's really difficult to figure that out. And I mean, I think we've talked at another one of these live streams about animal communication and the difficulty of knowing, even if you can solve the problem of, you know, the barking, the meowing, the tweeting, the whatever it is, even if we can solve the problem of the sort of the mechanical problem of an understanding of that, we still have to deal with the conceptual problem of, okay, so we're talking to the cockatoo, what are we going to talk about? What is our sort of shared kind of idea of what's worth talking about and how things work that we can kind of plug into? And that's a difficult problem, and it's a problem that is of relevance if you're interested in things like extraterrestrial intelligence and things like that. What do you imagine is the kind of common medium that you can talk about? All right, we're descending into philosophy here, so I'm only signed up to talk about science and technology. So let's move on to another question here. It's a question from Asa here. Why don't we make houses out of some kind of amber and then carve them? Gosh, I mean, people obviously have lived in caves at different times in history, and caves are naturally carved, typically by water flowing through rock. I suppose that you could make your own cave, and people will occasionally do that when they make some bunker somewhere. You drill out a bunch of rock. I think that when it comes to sort of the making of a house, for example, the technology of how to do that has remained pretty constant through human history, although houses get more and more and more elaborate and more detailed. And there are, whether it's, well, you just cut down a tree and chop it up and use that to make pieces of a house, or whether you're making some kind of cement-like thing, or whether it's fancy concrete with very elaborate material science, or whether it's engineered wood that is kind of wood that's been treated to be much stronger, or those kinds of things. But those are sort of details. I mean, there's some efforts in modern times to print houses. So, to have these giant 3D printers. So, I mean, the difference between, fundamentally, if you're going to make a plastic thingy, there is both the sort of, one way to make the plastic thingy is you have a mold, typically made of metal, and it is and you pour plastic into the mold, and the plastic forms into the shape that is in the gap in the mold, and that's how you make your plastic elephant or whatever it is that you're making. Is you've made a mold where there's a elephant-shaped hole in the mold. You pour liquid plastic into that. You let the plastic cool down and solidify, and then it will be in the shape of an elephant. You pull the elephant out. Now you've got a plastic elephant. That's sort of the traditional way from when plastics were invented in the 1930s and so on to today of making things out of plastic. The concept of injection molding is a little bit different. It involves you're kind of squirting plastic into this void, into this hole inside this mold, and then you take the mold apart so you can get the object that's in there. But so that's sort of one way of making things. Another way of making things is this kind of additive way of making things, which is how 3D printers work, where instead of saying, we'll just have this hole in this piece of metal and we'll squirt plastic in there, what instead one's doing is one's saying, let's build up the plastic just granule by granule, heating it up, and each granule is heated up and is sort of added to the growing thing. So when you watch a 3D printer do its work, you'll see a print head, and it'll be running around, it'll be squirting out little pieces of plastic, and it'll be gradually running around, and gradually the object that you're building will get bigger and bigger as it has things added to it. So people have tried to make sort of printers like that print houses, and I think there's a big effort right now to have some things made that way. And you can make all kinds of elaborate shapes and structures in that fashion. And I don't think we really know what the architectural story of houses will be in that form. One thing about houses is that people tend to have rectangular shape, roughly rectangular rooms. They have rooms with square corners and so on. And at times people have experimented, like there was a chap called Buckminster Fuller who was famous for experimenting with, the circular house and things like this. My impression is that the nature of kind of, it's all a complicated societal thing, because most of our furniture is made to be square-ish. And so if you have your round house, so to speak, it's unless one of the issues is, if you have a round house and you want to put a piece of furniture against the wall, the curvature of the furniture has to agree with the curvature of the wall, or it isn't going to fit. If you have a straight wall, you can have a piece of furniture of any length that is straight, and it will always fit against the wall. And so that's a sort of a problem with a circular house. And I think, until you kind of build the whole infrastructure, we're going to have standard shaped, houses that are always, 20 feet across or something, and we're going to have that curvature, and we're going to have everything fit on the walls. It's kind of tough to have that kind of thing work. But it is an interesting question to what extent one can sort of imagine, if one's making, let's say, houses out of completely different materials, let's say 3D printing them, what does that mean one can then build? I mean, in traditional architecture, people had become very used to kind of these ideas of the architectural form, and often the actual original reason why, columns would have this or that thing at the top was for structural reasons when they were first built in ancient times. But then people got used to sort of seeing columns that looked like that, and that was kind of the familiar and comfortable form of architecture that people saw. And for a long time, kind of people, it's, you know, when you see a piece of architecture that has a particular form, it kind of reminds you of all the other pieces of architecture you've seen of that form. And so in a sense, it's communicating something to see that architecture and to see, yes, that's a piece of architecture that was characteristic of buildings in ancient Rome or something like this. And it gives one sort of the gravitas of thinking about things in ancient Rome to see that this building, that's some government building or something, was built in that way. And so, I mean, that was kind of the people's, you know, the familiarity of what we saw from sort of our history in has been important there. I mean, it's similar to musical form, that there's a certain, you know, certain kinds of musical forms where people get used to them through history and they communicate something culturally, which if you just invent just a random collection of notes, it's not going to communicate anything culturally because it's just been created fresh. It doesn't have that, it doesn't have sort of burnt in history associated with it. And I think the same thing is true of architecture, that there's a certain sort of burnt in history associated with these particular forms. It's also the case that because we're exposed to nature, and nature has particular, in a sense, architectural forms. We have, you know, trees with leaves and this and that and the other. And so those are common motifs that we see in architecture, partly because those are things familiar from nature. And if we start saying, well, let's get rid of those, we don't need all that ornamental stuff in architecture, let's just have the plain flat wall, you know, the perfect flat thing, that feels very unfamiliar and uncomfortable perhaps to us, because we're actually used to the idea that in nature that doesn't happen very much. You don't see a lot of perfectly flat surfaces, perfectly geometrical forms and so on. I think it's a thing, you know, maybe 100 years ago or so now, people got very enthusiastic about the idea that, you know, let's derive architecture from science. Let's take these perfect geometrical forms that we understand in science. Let's say that's all we really need. You know, a building just has to be a box, and let's just make something that is a perfect box, because sort of science is telling us perfect boxes are a possible thing, and that's all we functionally need for the building. Let's make it that shape. And turns out, I think people don't particularly, some people think that's very elegant. Other people feel a bit uncomfortable because they're used to these forms, not just from the history of architecture, but also from nature, which is a lot older than architecture. They're used to certain kinds of forms and certain kinds of things that are familiar for how sort of trees manage to stand up and things like that. And yes, with, you know, steel and glass and concrete and all that kind of thing, you can make an architectural form that is very unphysical. I mean, in the end, it's got to stand up, but those materials are very strong compared to things that we're used to seeing in the natural world. You can make things that are very sort of anti-physical, but yet I think people will find them, I mean, it's communicating something to do that. And I think that so this question of, well, if you could make a building any shape, what shape should you make it, is an interesting question. And people, you know, in sort of the modern trend in architecture is, you know, architects always like it when they can sort of have a very, rather than just like, well, some architects like it, to say, instead of saying, let's make a thing that fits into the kind of tradition of this and that, let's make something unique. Let's just mold the thing in our own particular way. And I think some architects even like take clay and mold it in a certain shape, and then let's say, let's make the building this shape. And others will say, let's take some mathematical structure, sometimes even ideas of mine from looking at the behavior of simple programs and so on, and looking at the kind of geometrical forms they produce, and let's make a building that has these kinds of forms. Now, it's sort of interesting because in the most basic version of that, of let's make a science-based building in a sense, that is, just has this perfect geometrical form, that's one kind of thing. That's very unnatural in many ways. It's very different from what happens in nature. In the kinds of things I've studied a lot with simple programs, where you have even very simple programs that produce very complicated forms, that's actually the mechanism we think that nature is using to make those complicated forms. So in a sense, by making use of those simple programs, you are taking out the essence of what nature uses to make complicated forms, and you might be applying it for some particular purpose with some particular elaborate architectural constraints. I want to make a carpet with this pattern, but the room is this weird shape, and the pattern has to make sense given that shape. Well, you can run this cellular automaton rule and have it adapt to, it will naturally adapt to the shape of the room and make this form for the carpet, so to speak. And so in a sense, one gets to evade kind of the scienciness, the cold scienciness of geometrical structures and things by using, for example, simple programs. You can generate, in a sense, the complexity that we see in nature, but with certain constraints that might be useful for some architectural purpose. And people have tried building buildings like that. It's kind of interesting. And I've kind of always wanted to see a building where the building, from the overall form of the building right down to the detailed moldings and ornament, was all created with some particular simple rule. One of the features of that is, one of the things that tends to happen in architecture is there's a question: does the building make sense? Do all the pieces fit together? Same with a musical piece or something like that. Is there a logic to the whole thing? Or is it just, well, this person just added this random piece here and a random piece there? And one of the things that's certainly true of traditional architecture is that there are these kind of rules. Palladio was famous for inventing a collection of these back in, when was he? Maybe, when was he? About 1500 AD, I think. I might have that wrong, but I'll be embarrassed if that's wrong by 1,000 years, but I don't think it is. But in any case, the thing that he kind of gave these principles for what the typical shape of a room should be, what the typical kind of aspect ratio of height to width of a of something should be, and so on. Those are, that provides a kind of a framework in which you can kind of construct familiar types of buildings, or possibly buildings that resonate with the kinds of things that we see in the natural world. But so by creating a building from rules and having sort of consistent rules all the way through it, you have the potential to also have that kind of logical, making sense structure. And that's a sort of an interesting thing to try to do. But in any case, this question of sort of, it's an interesting question. What, one question that is sort of interesting is this question about, as you look at architecture over the course of time, and you see buildings that were built, I don't know, 200, let's say 200 years ago, and you see buildings that were built in the 1950s or the 1960s or the 1970s, it's always a little bit something when you can say, oh yeah, that's a very 1970s building. Oh yeah, now obviously there were architectural styles from much longer ago, but sometimes there's a certain, some of these styles have lasted better than others. And certainly some of these ones that I think wasn't helped by the fact that the materials which tended to be used, reinforced concrete and things like this, tended to not age as gracefully as some other, stone or brick or something like this. But in any case, it's also one of those things that I'm always amused by, that perhaps I shouldn't be, but some of these very elaborate architectural forms where people are saying, we're going to use the latest technology to build this building in a really arbitrary shape that has this weird roof that is, a very complicated, very complicated shape. The practical issue that always comes up is, does the roof leak? Because, a traditional roof, it's just, it has its little shape. And, if you go to the some parts of the world, the Alps, I guess, you have these much more pointy roofs because I guess it snows more and so on there. And you kind of don't want a bunch of snow sitting on the top of your roof. But if you end up with something where it's some very, very elaborate shape, now, I guess people have figured out this issue about roofs leaking by now. And now, no doubt, there are fluid dynamics simulations that figure out where rain is going to collect and what's going to happen if the wind goes this way or that way. But these are things which always have to go wrong before anybody figures out how to make them go right. I mean, it reminds me of a famous story of the talking of architectural problems, the Tacoma Narrows Bridge in Washington State. This is a story. It's a suspension bridge. So you may know that there are these types of bridges, right? You can build a bridge across a river or something, and you can just put it you can just have sort of each piece of the bridge hold itself up for itself, or you can have a suspension bridge where you have two big pylon type things at the two ends of the bridge, and then you basically hang the rest of the bridge between those two. And so when you hang it, you have this giant cable that hangs between those two things. And it's like a piece of string hanging between, you hold up two ends of a piece of string and the string will hang in a certain shape. And the shape it will hang in is called a catenary, and it's a particular shape. It's a hyperbolic cosine, as in the first approximation is the shape it forms. And it's just sort of dips down and forms that shape. And so when you build a suspension bridge, you put up these two big pylons, you suspend, you have this kind of giant cable, then you suspend the roadway or whatever you have from that big cable that is in the shape of a catenary. Okay, so good idea, interesting way to do it, requires, it's a interesting engineering thing. Okay, so there can be bugs. So if there's wind that blows through, across the bridge, one of the issues that can happen is that, let's say the roadway could be like a little bit of like a sail, the wind catches the roadway and it will push in a certain direction. Well, the problem is there will be a certain resonant frequency. So whenever you have a thing, a string, something like that, you pluck the string, there's a certain natural frequency that the string will go and vibrate with. And so similarly, in the case of a roadway, for example, there's a certain natural frequency associated with, for example, the twisting of the roadway or something like this. So the wind's blowing through, and if the gusts of wind are blowing through in a certain way, they will tend to excite the this natural resonant frequency in this roadway. And so the bad thing that happened with that particular bridge is, as the wind blew through there, the roadway started just twisting and twisting and twisting, and people, I think it was a bit of a tourist attraction, because like not every bridge has a weird kind of surfing type appearance. And eventually one day, needless to say, the thing twisted too far and just broke. And so that was sort of after that time. Every new design like that gets tested in wind tunnels or tested with computational fluid dynamics and so on to make sure that isn't going to happen. One of the things I believe, again, it's in engineering, after something goes wrong once, then people figure out, let's fix that. And then, after that bug has happened, then let's build a way to make sure that bug doesn't happen again. But even after that particular thing, I think they're building a road bridge in England across the Severn River. And although they had done testing of the final bridge, they hadn't done testing of the half-finished bridge. And so it ended up getting some nasty wind resonance type thing and made it, maybe it was just an excuse. This happened when I was a kid, I guess. And that bridge was like unbuilt for like a decade or something. And maybe it was just an excuse of some engineering or funding issue, but it was always said that was because of the fact that they hadn't tested for wind resonance of the partially finished bridge. And so they couldn't work on this bridge because things kept on sort of being blown around by the wind. All right, let's see. All kinds of questions. All right, there's one from Slayer here. How do traffic light systems work? Boy, diversity of questions here. Okay, so the basic, originally traffic lights were just on timers. And it's just like, you wait, the red lasts this long and then it goes green and then the cross street, goes and so on. In some places, there were very elaborate schemes, like New York City, for example, has this elaborate scheme where all the lights turn and change in a big wave going up the avenues in New York, and you can kind of see. And that means if you're going at a certain speed, you can kind of hit all the greens. But there was a time, I guess, in the 1960s, when it started to be the case that people made more automated traffic systems. I remember when I was growing up in England. Actually, I even had some interaction with the folks who were making those automated traffic systems. And what happened then was that they would have these strips in the road, which would essentially count cars. And it would be well, if there's a lot of traffic going this way, have the green stay longer than if it's going the other way, than if there's a lot of traffic going the other way. And so there actually in the end, there were these formulas developed that, well, first of all, there were these formulas developed for what the period of reds and greens should be based on the flow of traffic in different directions. And I'm not sure that there was very good, the people developed those theories and they kind of thought, well, people have measured this, and people who've measured it thought, well, somebody developed the theory. And I'm not sure how convincing either side of that actually was. But so there are formulas based on traffic flow rate for what the optimal, and I guess traffic speeds as well, on what the optimal traffic light timing is. But then people try to invent all kinds of schemes for getting traffic to flow properly. Like a good scheme is avoiding gridlock. So gridlock is you have streets where you'll have them at 90 degrees, so they'll be crossing over each other. And the problem is people are trying to go up the avenue, and which is going in one direction, and then across the cross street. And the problem is if the light turns red, but people are stuck in the intersection, then the people in the cross street can't go across, even though their light has turned green. And so there was kind of like, how do you avoid that kind of gridlock? Well, one very simple scheme that was invented is you paint these boxes on the road with crisscross lines on them, and you say, nobody can be inside that box when the light is turned the other color. Don't enter that box unless it is clear for you to get out of the box on the other side. And so that was a scheme that was invented to try and avoid that phenomenon. And then there are other schemes like, on freeway on-ramps, there's the, 1 car per green scheme of trying to space out traffic. Maybe I should explain one basic thing about traffic. So why are there traffic jams? So, you might ask the question, if you have a road, let's say it's just a single lane road, and everybody's going along the road at a certain speed, and then maybe there's something that's happening on the side of the road. Somebody put up a weird sign on the side of the road, and everybody's turning and looking at that sign. And so everybody slows down at that point. What will typically happen is, as you go back on the road, eventually you will get a traffic jam. And a traffic jam has the feature, so you might think everybody just slowed down by 5 or 10 miles an hour. So why doesn't the chain of cars going further and further back just slow down by 5 or 10 miles an hour? Why is there a traffic jam? Why do things get jammed? Why isn't it the case that that 5 or 10 mile an hour speed slowdown here just propagates backwards and everybody's going 5 or 10 miles an hour slower? Well, it doesn't happen because of an instability in traffic. What instead happens is that there are these waves that get produced that have an instability, and the traffic gets slower, slower, slower for a little while, and then it starts getting into stop-start traffic, and then eventually it gets completely jammed. And the reason for the stop-start thing, the ultimate reason for it is because drivers have a non-zero reaction time when, if they see a car in front of them slowing down, they do not immediately it takes them human reaction time, at least a third of a second, let's say, or longer, a few seconds often, to start slowing down. That's why, for example, brake lights are an important idea, because if all you were doing was sensing how fast you're going relative to the car in front of you, you would have to get pretty close to realize, oh, that car has stopped, I better slow down. But by having brake lights, you kind of know in advance that the car in front of you is slowing down. And then there was the innovation of, 10, 20 years ago, of having brake lights that were higher up on cars, so that even if you were not the car directly behind a car that was slowing down, even if you were a car or two further behind, you could still see that the car in front is slowing down, and so you can start to slow down. Both of those mechanisms have to do with reducing the time delay associated with driver reaction to cars in front slowing down, because it's that time delay that eventually leads to this instability. It's a kind of mathematical fact, not totally trivial, I think, to derive, of this instability that develops as a result of driver reaction times. And so that fundamental instability is what leads to sort of traffic jamming and the stop-start. Even though you might think the traffic will just go slightly slower, instead it goes into the stop-start mode. And by the way, it's a funny thing, but I worked a lot in the early 1980s on these things called cellular automata, which are these very simple computational rules, very simple programs where you just have a bunch of black and white squares, and you just say at each step, the black and white configuration of black and white squares will be updated according to a simple local rule. So I worked on these, and and figured out a lot about how different kinds of rules work and so on. Turns out I had actually worked a little bit on road traffic flow for completely other reasons. And years later, it turns out that the standard simplest model for road traffic flow is precisely one of these cellular automata that I studied. It's one called Rule 184. And it has the feature that it has, pretty nice representation of free flowing traffic, completely jammed traffic, and this kind of these waves of kind of stop start that happen in traffic. It's sort of the minimal model of traffic flow. Then there are more elaborate models of traffic flow that people have, and they get to be reasonably accurate these days. I think the tricky thing about traffic flow modeling is that it's a sort of multi-scale thing. Like you could say, where are all of the pieces of traffic? You're not going to model every car to 1 centimeter accuracy, nor do you want to just say, oh, well, we just have this number of cars in this part of the roadway. You have to have some intermediate thing. Actually, some people at our company invented some methods for doing a rather nice version of that a couple of years ago. That involves using graphs as a way to represent different sort of scales of traffic flow and so on. One of the things that's really surprising is how little is known about the precise dynamics of how cars follow cars and so on. There are just a couple of examples where people have really measured one freeway somewhere in California where for 2 hours, people traced exactly where every car goes. I mean, there are tons of places where there are cameras on freeway bridges or whatever else, where they're measuring the overall rate of traffic flow. But this very detailed thing about exactly which car went where and when did it change lanes and all that kind of thing, there's surprisingly little data on that. And so when people try and make detailed models of traffic flow, there's just not a lot to go on. I mean, these days, there's obviously a lot of information about overall traffic flow from cell phones in cars where people are, connected to some navigation service and it's sending back data on well, or even not connected to a navigation service actually as well, for better or worse, where it's sending back data on there are this number of iPhones that are stuck in this traffic jam in this place, and that feeds back into a bunch of traffic information. In the end, it's there's a certain societal good associated with that, because basically in the end people spend less time in traffic jams because the routing systems can figure out how to send cars to places where there aren't traffic jams, and that's presumably good for people. I mean, it's an interesting question is when you have a traffic jam, for example, is there any way to break a traffic jam? Is there any way, let's say there were self-driving cars in the traffic jam and or associated with that sort of traffic situation, is there a way to have like seed cars somewhere which drive in a particular weird way and which cause the traffic jam to be broken up? I suspect not, because I suspect that the instability of traffic jams is an instability that will happen, and there's no obvious way to fix it. Now, of course, there are things people do, like, for example, if it becomes the case that there are enough self-driving cars, there start being lanes for self-driving cars and so on, they will have completely different characteristics in terms of this issue about driver reaction times and so on. One way they'll have a different characteristic is that self-driving cars can communicate with each other. I mean, it's like, drivers don't really communicate other than by seeing brake lights and things like this. Drivers are not, unless they're truck drivers using radio and things like that, but then that's a different kind of thing and not at this more detailed level. But if this idea that you can have autonomous cars which are really directly communicating, where the car, 30 cars ahead is saying, I'm going to make this change, and then that propagates to cars far back. And potentially there you can imagine, I think it will work, to have cars zipping through at high speeds where you don't have this phenomenon that's the result of human reaction times of having traffic jam formation. But this question about sort of how do you optimize, I mean, what's the optimal way to set up traffic timings? I would say there's a certain amount of knowledge about that, although as soon as there are autonomous cars, and particularly communicating autonomous cars, all bets are off. There's no theory for that. All of the work that's been done in traffic engineering tends to be based on these models that have been developed over the course of time, where people have gradually tweaked the models to accurately represent traffic behavior. And it's a bit different in different parts of the world where people have different conventions about, how aggressive are you as a driver, and that has an effect on the parameters for traffic flow and so on. And so, you can expect that there are different dynamics. I don't know the details, but I'm sure in different parts of the world, the traffic light timings are differently set up because there are different expectations about, to what extent will people try and run through yellow lights, and to what extent will this happen and that happen, and so on. I always found it interesting that, I grew up in the UK, where the traffic light story is different. Like, for example, when it goes from red to green, in the US, it just goes red, and then boom, it's green. Everybody's going. In the UK, it goes red to yellow to green. Actually, it goes, my gosh, it's too long since I've been there. I think it's red and yellow at the same time. Is that right? Yeah, I think it's red and yellow at the same time, and then green. Back in the day, people used to say that's the yellow is when you put your car in gear for a stick shift car. And you're sort of getting ready to go, and then it's go. And I suppose, I don't know whether it's a sign of different national character that in the US, it's red, and then boom, it's green. Everybody goes. Whereas in the UK, it's like, well, get ready to go, and then go. I don't know. Let's see. Oh my, so many questions here. Okay. Huh. Someone's asking, do I prepare any of these answers? No, I prepare nothing here. I'm just look at the camera and talk. So I apologize if things are more scrambled than they should be. Although the thing that's been great for me about doing these live streams is I think I can measure that I have become a better explainer of things as a result of doing this. Okay, let's see. We've got another one here from Gist. How are the magnetic north and geographic north poles related? Well, so okay, the Earth spins on its axis, and it changes the speed at which it spins slightly, and that's why there are leap seconds and all kinds of weird things like that. But fundamentally, the Earth is spinning on its axis. Its axis is 23 degrees away from the, it's orbiting around the sun, and its axis is tipped 23 degrees from the direction in which it's going, and the plane of the ecliptic in which it's going around the sun. And that 23 degrees is what leads to our seasons and a bunch of other effects about the Earth. But the axis on which the Earth is turning, that's remained, well, it remains almost in a constant direction. It precesses. It's called the precession of the equinoxes. That's at least the primary effect. It moves slightly, it turns around slightly. And that's a 23,000 year precession period, I think. So, the ancient stars recorded by, Hipparchus or Ptolemy or somebody did look a bit different from the modern stars because of precession of the equinoxes. But fundamentally, the Earth is rotating on a definite axis. Okay, that's the rotation of the Earth. Then the question is, what about the magnetic field of the Earth? So when we have a compass has it's a bar magnet, and the bar magnet has what's usually called its north pole and what's usually called its south pole. Those are just names for the different, the magnetic field is going in a different direction for that bar magnet, and the magnet is attracted towards the sort of corresponding pole of the Earth's magnetic field. So I should explain, the Earth acts like a giant bar magnet. So a bar magnet has, how does a bar magnet work inside? A bar magnet has a bunch of iron, let's say it's an iron magnet, not a rare earth magnet, iron atoms, which are all lined up in a certain way. And it is a feature of iron atoms that they have a certain magnetic moment. They are like tiny, tiny bar magnets. And a piece of magnetized iron, all those little tiny atomic bar magnets are all lined up. And so what happens is the magnetic field it's aligned in a particular direction. It goes out from, let's say from south to north, and then comes out of the magnet, kind of makes this big loop, and then comes back into south again. The rule for magnetic fields is every magnetic field, at least if it's a static magnetic field not changing in time, every magnetic field just has closed loops of magnetic flux. And that means that, for example, when you put iron filings around a magnet, you'll see they will collect in the directions of these magnetic field lines. It's the feature of magnetism that magnetism always has closed loop field lines. When you're dealing with the electric field, electricity, when you're dealing with electric charge, it works very differently. An electric charge produces electric field lines, and they all go outwards in a kind of hedgehog shape from the electric charge. So they all start at the electric charge and then all go outwards. You can have an electric dipole where you have a positive electric charge and a negative electric charge, and then there'll be some electric field lines that go from one charge to the other, and others that form that same kind of loop going around the outside, so to speak. One feature of magnetism is that, so far as we know, there are no magnetic monopoles. There are no magnetic charges. So the smallest magnetic thing you can get is a magnetic dipole, something like a bar magnet, or a very microscopic bar magnet, like one of these atomic bar magnets that is an iron atom in what forms a lump of magnetized iron. Okay, so that's sort of how, so the Earth's magnetic field is more or less like what you would get from a giant bar magnet. How does the Earth end up having a magnetic field? It has to do with the liquid core of the Earth, and it's believed that, oh, I should explain another thing. One way to produce some, okay, I was jinxed by somebody saying that these explanations were clear and initially well thought out. I forgot a piece of this. So one way to make a magnetic field is from, let's say, the elementary magnetic dipoles of something like an iron atom. Another way to make it, which is actually also related, is from an electric current. So if you have a loop of wire, that loop of, and you have an electric current going around that loop of wire, that means there are electrons basically moving through that loop of wire, moving charge around that loop of wire, then it is a feature of electromagnetism that you get a magnetic field, and the magnetic field kind of has its field lines going up through the loop and then coming around the outside and back through the loop again. So that's how a typical way you make an electromagnet is with a solenoid, and a solenoid is just a coil of wire that can be, it's just coiled around in a big spiral, and it's just wound around some core. And when you put an electric current through the solenoid, it's all kind of going in the same direction. All the loops are going in the same direction, and it will produce a magnetic field that is going through the solenoid in the direction at 90 degrees to the direction of the loop. So, okay, so moving electric charges or electric currents produce magnetic fields. You can think about that being the way that a magnetic field is made, well, at least at the level of the electrons going around the nucleus in an iron atom. There is also another effect, which is that electrons themselves have an intrinsic magnetic moment, which you can't really think about as the result of a circulating electric charge. It's an intrinsic feature of electrons that they have this magnetic field, and not something that comes from circulating charges. And that's ultimately where the where lots of magnetism in magnetic materials comes from. But so anyway, one source of magnetism is circulating electric currents. Okay, in the liquid core of the Earth, there are thought to be circulating electric currents, and they're thought to be what produce the magnetic field of the Earth. And it's kind of like there's a big loop of current going around in the Earth, and that's producing this big magnetic field that's like a big bar magnet, or like what you would get from a solenoid. And that so the one question is, if it's a bar magnet, what direction is the bar magnet in? Well, you might say the bar magnet might be aligned with the rotation axis of the Earth, but it isn't quite. It's a little bit off. I think it's right now about in the north magnetic pole of the Earth is somewhere in northern Canada. I think it's like in Baffin Island or someplace like that these days. And the north magnetic pole is that's the that's the Earth's magnetic field is not exactly a pure bar magnet field, but it's a pretty good approximation. And it's as if that bar magnet is pointing up into northern Canada, not precisely to the north rotational pole. So one thing that happens is the magnetic poles of the Earth, the magnetic field of the Earth actually changes with time. As those currents in the mantle shift around, the magnetic pole of the Earth moves around, and it moves a significant amount. I mean, in a century, it will move a lot. It will move enough that you really have to pay attention to it if you have, let's say, land records that are based on magnetic information. I think it's not very many centuries ago that the magnetic pole was somewhere in Europe. And the magnetic pole has even flipped around. So the North magnetic pole was even in the southern hemisphere back in the day. And one can tell that by looking at rocks that solidified at a certain time in history. And you can see that their magnetic fields were that when they generated a spontaneous magnetic field, when they solidified, that it was in a different direction. And that spontaneous field will have been determined by the magnetic field of the Earth at the time they were formed. So magnetic poles of the Earth move around a bunch. And presumably the reason this happens is in the liquid core of the Earth, which is where you get to if you just drill down maybe 50 miles under the crust of the Earth, you get to the liquid mantle of the Earth. What happens is there are places where you have convection currents. So convection is the phenomenon. Okay, so for example, when you have air, for example, when you have hot air, it has a lower density than cold air. And so hot air, in a sense, floats on cold air. But if you suddenly heat up some air down here and it's below some colder air, that hot air will want to go up and kind of float on the colder air. It will want to rise. So the hot air rises. The cold air, because it's heavier than the hotter air, it'll want to sink. So you get this phenomenon where the hot air is rising, the cold air is sinking, but then, of course, the total amount of air has to remain the same. So when that's happened, you still have to have this loop as the air cools down or whatever. If it was hot air and it sank, then it cools down, and then as it heats up again, let's say if you're heating it from underneath, let's say it fell down because it was cold, then it was heated, it got hotter again, then it goes back up. And you end up getting these cycles, these convection cells, as they're called, that form where there's hot air rising, cold air falling, and you get these definite cells. You can sometimes see these kinds of things. If you're heating some fluid, you'll actually see convection cells where there are regions where the air is where the fluid is coming up and then going down again. Actually, you'll get, even in very bizarre cases, you'll see rocks that, well, the convection cells tend to be these kind of hexagons that pack together. And at least when the rate of convection is sufficiently slow, that it's very regular and laminar and doesn't have kind of complicated turbulent behavior. And sometimes you'll even see that in rocks. You'll have these what are they called? Devil's Causeway type formations where you have these hexagonal shaped rocks that were presumably formed by these kinds of convection cells. But in any case, in the mantle of the Earth, there are presumably convection currents and convection cells, and presumably it's the electric currents associated with those convection cells that lead to the formation of the magnetic field of the Earth, and those convection cells gradually move around as a result of fluid motion in the center of the Earth, and that's presumably why the magnetic field of the Earth moves around. So that's of course, it's not quite as important these days because people tend to navigate not with magnetic compasses, but with GPS. And so this sort of correction between true north and magnetic north that people are always concerned about, like, when you would set a compass, you would have to set the correction between true north, the actual north associated with the rotation of the Earth, and magnetic north associated with the position of the north magnetic pole of the Earth. Let's see. There are a lot of interesting questions here. I'll try a couple more here. There's one from Arvin. How come oil is deposited in Arctic regions? Oil is deposited everywhere. You know, what is oil? Oil, so back in the Carboniferous period, when was it? 300 million years ago, maybe, of that order. Is that right? Roughly that, a few 100 million years ago, before dinosaurs. The Carboniferous period was a time when plants suddenly appeared on, you know, in the on land, and they were sort of a super good idea at the time. And so plants, trees, whatever, covered the earth with you know, with this, all of this very lush vegetation. And I think there started to be critters like dragonflies and things. I think they were around even at that time. And you get this kind of nice vision of the Carboniferous forest, so to speak. But, even the name Carboniferous, carbon bearing, is kind of an indication of what's coming, because what happened is that all of that lush vegetation that existed at the time when plants discovered that they could grow on land. Before that, there'd been plants in the oceans, algae and things like that. But the sort of mechanism of how you succeed in being a plant on the land and doing photosynthesis and pulling water from the ground and all this kind of thing, all the inventions that had to be made to make plants work on land, that suddenly happened in the Carboniferous period. And because there wasn't sort of a lot of competition for resources, there were just a lot of plants on land on the earth. Those plants ended up getting fossilized. They ended up getting kind of crushed into in rocks, and all of the stuff, the carbon and so on that had existed in those plants, all the complicated hydrocarbon molecules that those plants had made, end up turning into, as they get crushed by pressure in rock, they turn into oil. And so that's what makes these oil deposits. Now, over the course of geological time, those oil deposits get covered by things that get covered by things, et cetera, et cetera, et cetera. But kind of any place where there was land in the Carboniferous period, you can expect that there will be kind of crushed plants that will have potentially turned into oil. Now, then the question is, how deep is it? How can you find out where it is? All those kinds of questions. And this question of sort of how much oil is there in the world is a difficult question. And I remember people saying, I don't know, 40 years ago or something, oh, there's only this amount of oil in the world. It's like, do you really know that? And well, no, actually, because you know, it could be that there is oil, but it's much deeper, or it's much more enmeshed with rock. You know, sometimes there'll be actual reservoirs of liquid oil, and sometimes it'll be very much in, you know, sort of kind of in porous rock. It'll be very sort of interwoven with the structure of the rock. There'll be little pieces of oil, but they'll be sort of very much in the rock, and you have to kind of squash the whole thing to get it out, so to speak. And so it's this question of sort of how much oil is there. Well, you know, it was all made in a fairly limited period, in the Carboniferous period, and so there's sort of you know, there's some knowledge from that. But this question of how much oil is there, where is it, how deep is it, that's not an easy question to answer. And there's a lot of effort that's been put in over the years, people looking for oil. And, you know, part of the strategy is you drill a hole here, you drill a hole here, you see whether there's any oil down there, you drill a hole a certain depth, a mile down, whatever else it is, you figure out, is there oil there? And then you say, well, what's the chance that if there wasn't oil here, that if I drill another hole 20 miles away, that there will be oil there? And there's an elaborate kind of theory of statistical theory. In fact, we're just adding, in the latest version of Wolfram language, we're adding this this whole area of spatial statistics is getting well developed, and it's kind of interesting because there are ideas in spatial statistics that directly come from mining and so on. There's a thing called kriging, which was invented by an engineer, a mining engineer who was interested in gold deposits, and it's a way of sort of giving you an estimate of what the density, given that you've drilled certain holes in certain places and you've found something, you haven't found something, it's a way of estimating what the likely density of the stuff you're looking for is in places other than where you actually drilled the hole. But this is kind of a very much a story where you can expect to use machine learning and all kinds of statistical techniques to say, given that you drilled a bunch of holes, what's the chance that you will actually hit oil, strike oil or something in a particular place, based on the holes you've drilled and so on. And there's both an elaborate kind of geological theory and elaborate financial theory of, how many holes do you drill and how much does each hole cost and what's the chance, how deep should you drill them, et cetera, et cetera, et cetera. But that's been kind of a strategy, but it's hard to know what the eventual answer to how much oil is there. And it is probably the case that there is more oil, it's deeper, it's harder to get out, it's more expensive to get out. It's sort of a complicated thing. But the question of why is there oil in a particular part of the earth, it's, because most places on the earth, there was once a carboniferous forest and it got squashed into oil. And there are details about whether the oil is really formed, and it depends on the geology. And that's why oil companies employ a bunch of geologists to figure out, what's the likelihood that in this particular geological formation, there will be oil formed, and will the oil be gettable out, and will it have mixed with the rock in this way or that way, and so on. I mean, I remember many years ago, I once did when I was much younger, I once did a consulting thing for an oil instrumentation company. And so I learned a certain amount about the problem of how oil and water mix in porous rock, and the question of just how what you would need to do. And in fact, I did come up with some ideas, which I don't know whether they were ever implemented, about how you could enhance the, I've always felt that, perhaps unreasonably, that my small contribution to enhancing the rate at which you could get oil out was vastly exceeded any possible oil that I would ever use in my lifetime. But I don't know if that's a good calculation or not. But in any case, I mean, it's a general rule that, countries with bigger land area end up with bigger mining assets, just because it's just a pure statistical question. If you have a giant land area, Australia, the US, Russia, whatever, you have these big land areas, you'll tend to have, there'll tend to be more stuff that was buried somewhere there. And one of the confusing things, I would say, probably more so, particularly for minerals, is this question of, somewhere there will be tellurium buried, somewhere there will be europium buried, somewhere there will be gold. And somehow in the formation of the earth, there were all these different deposits of these different things where, for whatever reason, as the earth condensed, and I'm not sure how well understood this is, these particular materials concentrated in particular places. And now, there'll be a city in Colorado that's named after, I don't know, Telluride or something, or molybdenum city or whatever, that's named after particular minerals that happen to exist at that particular place in Colorado, let's say. And so I think that's an interesting phenomenon. There's a sort of collecting effect, and I'm sure that happens to some extent with oil. But oil is not, its origin is organic, and it was from the successor plants on the land. Yeah, I was going to say today we've had all kinds of interesting questions, and I've only got to a small fraction of them, but I would be interested in people's feedback about ways that this series might evolve. I will point out that all the previous versions, previous episodes of this are up on the web, and there's a nice website, maybe somebody can paste it in chat, where we've run all of these episodes through our video and audio processing system. And that means that we've got word clouds of the top words said. So I'm sure that the last few minutes, oil will be a big word that shows up there. And so you can tell a little bit what I've been talking about in these different episodes, and there are also some actual questions which are listed there. And so if you're interested in finding things that I might have talked about in the past, it's a good way to do that. I'm kind of trying to always talk about something new and different each time, I think the diversity of questions is very high. The space of possible questions is very large. So in a sense, it's easy to start talking about different things. But I would be interested in feedback about suggestions about how this series might evolve. I might say that I have been doing this on Fridays at this time. On Wednesdays, alternating between different weeks, I've been doing a series about Q&A about a history of science and technology, and also Q&A about business innovation and managing life. I'm trying to fit in more different kinds of things, but I also have a lot of other activities. I also have live streamed a bunch of a bunch of other things we've live streamed. Like yesterday, I live streamed a discussion I was having with a physicist named Lee Smolin, and that was kind of a different series. And we've also been live streaming a lot of our working sessions, working on physics project, and also working on software design and those kinds of things. But I'm thinking about a variety of other kinds of live stream things that I might do. In particular, I write quite a lot of pieces for my writings, kind of blog-like thing. I've realized that I don't actually give talks based on the things I've written there, and I don't specifically answer questions based on the things I've written there. Some of them are somewhat technical, but many are not. And I think I may start a bit of a series kind of talking about the things that are in those posts. Maybe even basically, we've made podcasts from some of those posts, and maybe I'll even do sort of a reading of the post followed by Q&A about the post. And the reading will turn into a podcast and so on. But so I'd be interested in people's feedback about, hey, is this a good idea? Is this a bad idea? It's been the fact that I even started doing these science and technology Q&As, which I found fun and I found really interesting to do. This was a very coincidental thing because I figured when the pandemic was starting, I knew there were all these kids who were out of school, and I sort of heard from some people, oh, these kids have nothing to do, and they need content of various kinds. And so I was like, okay, well, I can at least try and answer science and technology questions. It's fun for me, hopefully educational for kids, and that's how this series got started. Let's see. Well, I think probably we should wrap up in a moment here. Is there anything I can see here that we might? You see, there are questions here that are coming in. Let's see. All right, there's a question from William here. Let me try and see if I can do this one. This is a slightly technical question. Could I explain what eigenvalues and eigenvectors are and what you do with them? Okay, so let me give you an example. So let's say you have a bunch of, let's say, websites or just places, and they're connected by links on websites, roads between places, things like that. You can form a mathematical graph, a network that says this thing, sometimes you call them states because you can represent the state of a system by a particular node in this graph, is connected to another node in the graph, it's connected to other nodes and so on. You form this network, okay? So a question would be, if you start off if you start people off at certain websites, you randomly scatter people across websites, and then you say, let me now have people follow all the links from that website. And they go to other websites. Or same thing with places, all the people start in that place and they all, they randomly go down the roads from that place and they get to another place and so on. So the question is, if you keep doing that and you keep, let's say, having these things randomly run around on this graph, where will things collect? Will it be the case? There might be some place where everything collects in that place. There might be another place where everything is gone from that place. So what you can think of is, as you successively sort of iterate, you go to look at sort of more and more places where more and more, where does it collect? That the sort of the thing it collects is, this is one way to explain it, is the largest eigenvector. So you can think of it just to making a vector, a list of numbers that correspond to how many people were there at each of the nodes of this graph. And as you keep iterating, sort of running people through the graph, eventually people will collect in a certain configuration, and that configuration is one of the eigenvectors of the graph, or of the matrix that represents the graph. Okay, let me explain that. So, okay, vectors. Often people think about vectors as being, a direction in space, or, some base and then some direction in space. But at a very simple structural level, you can think of a vector as just being a list of numbers. It's just, let's say if it could be a three vector, which is a list of 3 numbers, or it could be a 10 vector that's a list of 10 numbers, or whatever else. You can think of those numbers as corresponding to coordinates of a point, let's say in 3-dimensional space, if there are 3 numbers, or you can just think of it as a list of numbers. So you can think there's a list of numbers. Okay, what happens if you have a list of lists of numbers? Well, you can arrange those if you want to in a 2-dimensional grid, but a list of lists of numbers you can just think of as, well, it's a list of numbers, but it's also often called a matrix. A matrix is this kind of array of numbers, a rectangular array of numbers. You can think of it as a list of numbers. Okay, so what's the point of matrices? Well, matrices are useful just as lists of numbers. That's a convenient thing to have around. Like that list of numbers might be, oh, I don't know, let's say each row represents, each sort of inner list represents the coordinates of a point in 3-dimensional space. Then you might form a matrix by just having a collection of essentially those vectors. That might be one interpretation of a matrix. Okay, there's an important interpretation of matrices, which was the early one they were invented by a chap called Arthur Cayley in the 1870s, I guess. Although they're sort of an obvious idea, but they hadn't come up before that time. But in their original invention, they were invented for reasons very different from these kind of structural reasons of just whole arrays of numbers. So instead, they were originally invented because of a kind of mathematical setup. So I mentioned that a list of numbers, like 3 numbers, could represent a point in 3-dimensional space. So a question is, if you want to say, you got a point in 3-dimensional space, and you want to, let's say, rotate that point. You've got this position in 3-dimensional space relative to some origin. You want to rotate that position by some angle. You want to sort of rotate it, I don't know, 30 degrees in the such and such direction. Okay, what does that rotation do to the vector, to this list of coordinates of the original point? How do you make that transformation? Okay, so there's a trick. That transformation can be represented by a matrix. And that matrix, in the case of 3-dimensional rotations, is a 3x3 matrix. And what's going to happen is that 3x3 matrix, there's a mathematical operation that you do where you take that 3x3 matrix and apply it to this vector of length 3 and get out another vector of length 3. And that particular operation, it at first seems kind of unnatural, but what you do is you take the matrix, which is a list of, you can think of it as a list of lists, and what you do is the first row, the first inner list, you take that inner list and you basically combine it with all the elements in this vector that you're trying to transform. And then that gives you one result. You take the second row, you combine it with all the elements in the vector, it gives you a next result. Then the third row, and that gives you another result. Those 3 results are the transformed version of the vector. How do you combine the elements in a particular row of this matrix with the elements in this vector? So there are 3 elements in one of the rows of the matrix. There are 3 elements in the vector, let's say. What are you going to do to combine them? Well, you form so-called dot product, scalar product. And what you do is you simply take those 2 lists and you take each element, take the first element of the thing from the matrix, first element of the thing from the vector, multiply them together, get a result. Do the same thing for the second one, do the same thing for the third one, then you add up all those results. So maybe I've been using our Wolfram language too long, but to me, I just think of taking those 2 lists and you literally multiply them together, and then they will element-wise multiply, and then you take the result of that and you find the total of that, and that's the result. Okay, so that's sort of a mathematical trick that you can take this matrix. There is a matrix, so-called rotation matrix, that you can construct that represents a rotation through a certain angle, and whatever vector you feed it, it will take, and you do this operation I just described, this matrix product operation, and then you get out another vector, and that other vector will represent the result of rotating the point in that first vector by whatever angle you specified. And so rotation matrices are one example of a 3x3 matrix, but you can put whatever junk you want into that matrix. So one of the questions is, for many kinds of junk that you can put into that matrix, it will be the case that the matrix times this vector will produce something which is not necessarily that vector itself, but that vector multiplied by some constant. So it's as if that matrix, okay, so if the matrix was the identity matrix, let's say 3x3 identity matrix is just 1, 0, 0, 0, 1, 0, 0, 0, 1. That means that in the first row, when it combines itself with a vector, it picks out just the first element of the vector, so that becomes the first element of the result. Second row picks out the second element, that becomes the second element, and so on. So the identity matrix just keeps a vector and makes it and just produces the same vector again. You multiply a vector by an identity matrix, you just get that same vector back again. Okay, so there's sort of a generalized version of that, which is, what if that matrix, instead of producing the exact same vector again, produced something which is a constant multiplied by that vector? So that's the case where what one says is that constant is the eigenvalue, that constant. I'm sorry, let me be less confused. So for a particular vector, given a matrix, there will be a particular set of vectors which have the property that the result that you get by multiplying by the matrix is just a constant times the vector that you put in. The vectors for which that's the case are the eigenvectors. The constants are the eigenvalues. You know, I'm not sure this is the best way to explain this. It may be better to try and explain this geometrically, but let me say the sort of the big picture is eigenvectors are sort of things you get when you do a transformation, you sort of get the same result after you do the transformation as before. So the thing as I was explaining about all these things sort of moving around on a graph, what happens there is when things have been going for a long time, going for even longer doesn't make much of a difference. So in a sense, what's happening there is that you're seeing the eigenvectors come out as a result of, it's just sort of, the thing has happened for a long time, and so it's reached this point where that is the result of the transformation, and applying the transformation again, that is having time run even longer, doesn't make a difference. And that's kind of the big picture of eigenvectors, is this, what you get as where it no longer changes when you apply this operation. And so, for example, when you look at something much more complicated, which is something like, I don't know, you've got some drum and it's a certain shape, and you play the drum and you ask the question, under what circumstances does the shape of the drum correspond, what are the possible sort of shapes that the drum can take on while being consistent with the fact that the drum head is sort of locked down on the edges of the drum. And those shapes are often called the eigenmodes of the drum, the shapes that you can take on that are consistent with these boundary conditions and are consistent with the equations that describe the structure of the drum. Those are the eigenmodes. There are also eigenvalues, which correspond to the frequency of that particular vibration of the drum. I shouldn't have taken this as my last "that'll be easy" question, because this question, it's a lot easier if I was typing this into Wolfram language. It would be a lot easier to explain this, and I think I'm so this can be considered an experiment in my effort to explain something which is not actually very naturally explained in words. But so hopefully that gave some sense of what eigenvalues and eigenvectors are. There are lots of things to say to that. All right, I'm going to wrap up now, and please remember, do tell us your feedback about rejiggering these live streams. You can send it to outreach@wolfram.com if you want to send email, or you can just respond on chat on whatever platform you're using. And thanks very much for lots of interesting questions today. We will save the ones that I haven't gotten to up for another time. So look forward to talking with you another time